Good morning, guys. Good to see you. It is Wednesday, October 7th. We are discussing enzymes. It's chapter 6 in our textbook. Can you hear me well? Yes?
Yes.
Okay, thank you. So we talked about how enzymes worked, We talked about how they reduce the, how they provide a different path for the reaction, right? And reduce the activation energy overall, and thereby accelerate the reactions. We talked about different ways the enzymes accomplish that. And so today and probably on Friday, we're going to talk about enzyme kinetics. So as I mentioned to you, this chapter has a lot of math in it. And math is not very difficult, but compared with the rest of the chapters, it has probably the most of it. So so let's get to it. So as usual, if you have any questions, just let me know. Okay, let me share the screen. Share the screen. Now, just to mention to you that my computer I'm already mentioned to you that my laptop started to crash recently from during Zoom meetings. I don't know what the problem is. If that happens again, it shouldn't. It hasn't happened in our class yet. But if it does happen, please, it'll take me a few minutes to come back to the Zoom. So the lecture is not finished. Just go back to the same Zoom session. Just give it 6 or 7 minutes maybe to for me to restart my computer, and we'll pick up from where we finished. All right. Okay. So so what is enzyme kinetics? So basically kinetics, remember kinetics is the rate of the chemical reactions, right? So thermodynamics are energies, kinetics are rates. Right, so we talked about a bag of sugar, right? So thermodynamically, the bag of sugar should burn very easily, right, to produce carbon dioxide and water. Lots of energy should be released. But kinetically, it's a very slow reaction. So the bag of sugar can sit on your shelf for a very long time and nothing will happen. So for a reaction to be successful, both kinetics and thermodynamics have to play a role, right? And so the rate of the enzymatic reaction is affected by, so obviously the enzyme, right? The enzyme has to evolve to perform a particular reaction. Now substrate, if you change the structure of the substrate, reaction may slow down or accelerate. Different effectors. So here we talk about allosteric inhibition and so on and so forth. And temperature. All right, so temperature, we know that.
Dr. Kornienko.
Yes.
Are we going to skip the chymotrypsin and the peptidoglycan?
Yeah, so what I've done actually, yeah, guys, I apologize for that. I rearranged the slides. So after we finish I moved the kinetics ahead of the chymotrypsin and lysozyme.
Okay, perfect.
So in your lecture slides, if you can just put that behind the kinetics. And so we're going to discuss that. It's just that I didn't want to break the, because that material will take half the chapter, and I want to have the full lecture of kinetics today. All right, so the two people who actually put forward the kinetic theory that we're going to talk about are Michaelis and Menten. And so oftentimes this kinetics that we're going to discuss today is known as Michaelis-Menten enzyme kinetics. All right, so what do we need to study? Well, first of all, it provides quantitative description of biocatalysis, right? So far we talked about all these hydrogen bonds, active site, lock and key, induced fit. But what about quantitative description, right? So what about different inhibitors? Which inhibitor is better, right? So kinetics will tell us which inhibitor will be better, which enzyme is better, right? So determine the order of binding of substrates. Well, this is a minor thing, but very important as well as you design the, let's say there are two substrates that the enzyme catalyzes the reaction. So which one binds first, this one or that one? Again, important for, let's say, optimization of the enzyme function or inhibition of the enzyme. Elucidate acid-base catalysis. Understand catalytic mechanism. So very crucial, right? So how do we know that the mechanism is such and not a different one? So you know from organic chemistry, mechanisms are crucial to understanding chemical reactions. And with enzymes, again, if you want to inhibit an enzyme, you need to understand how it works and obviously find effective inhibitors. Understanding the regulation of activity. Okay, so that's all about, again, either make the enzymes more effective or inhibit them. All right, so we're going to start with the model mechanism. So let's do that. So I have a blank page. So first of all, we're going to start with the term for reaction rate. So V naught. So this is going to be initial velocity. We're going to deal with initial velocity. Why initial? I'll tell you in a moment. Now remember, the rate of any kind of reaction will change depending on the rate of the starting on the concentration of the starting material, right? So the higher the concentration of the starting material, the faster the reaction. So here with the enzyme, it's the concentration of the substrate. So as the reaction proceeds, right, the concentration of the substrate changes. So you start with a high concentration of substrate and then it drops. So the question is, which concentration of substrate do you use if it changes? And so the problem is solved by just taking into account the reaction rate at the very beginning of the reaction, when very little of the substrate has been converted to the product. If you think about, in general, I mean, the whole point of enzymes is that they're present in small amounts, right? Catalytic amounts, tiny quantities, like 1,000,000 times less than the substrate. And so at the beginning of the reaction, very little of the substrate is converted. And so if you measure the reaction rate at the beginning of the reaction, basically it's this concentration of the substrate has not changed much, okay? So let me write this down. So only small amount of substrate is converted to product. Okay, and so for the concentration of the substrate, you can use the initial concentration of the substrate. So you don't really need to know what it is at that particular moment, because very little of it is converted. So you can just use the starting amount of the starting concentration of the substrate. So that simplifies things a whole lot. So the second assumption we're going to make, so we're going to use initial velocity. The second assumption we're going to make is the actually how the reaction occurs. So we have the enzyme reacting with the substrate. K1, and this will be an equilibrium process, and this will form an enzyme substrate complex, which will then undergo the chemical reaction, and here we will simplify by saying that the product, once it's forms, immediately dissociates from the enzyme. Okay, so it has lower affinity for the enzyme and immediately comes off. Now it's a simplification, but it works for most of the enzymes. So we'll stick with that. And so based on this equation, then our V naught, okay, V0 equals, so where does the reaction occur? Reaction occur in the second step here. So the reaction rate will be equal reaction constant from what we know from kinetics, right? Times the concentration of the enzyme substrate complex. So this is our beginning of our equation for the reaction rate. That's how we're going to measure it. So here we don't really know either of these, right? One thing that can simplify our task here is that the concentration of the enzyme substrate complex, again, we don't really know what it is, right? And also one thing to keep in mind, I'm just going to put some expressions on the slide which makes sense, which we're going to be using. So the concentration of the free enzyme will be equal to the concentration of the enzyme total. Right, so basically how much enzyme do you put in the reaction mixture minus the concentration of the enzyme which is occupied with the substrate. Like so. All right, so here obviously yes, so the enzyme total is how much enzyme you put into the reaction mixture, right? So we know that. But then the question you may ask, okay, so we don't know the enzyme at any particular time, but we also don't know how much of the enzyme is occupied by the substrate at any particular time. So that doesn't really help us very much. So we need to find out how much of this is present in the reaction mixture. And so for this, we need to generate two expressions. So again, so this will be forming during the reaction, and this will be decomposing, right? So it forms in the first step, you can see here, right? So the enzyme comes together with the substrate to give enzyme substrate complex, and it breaks down as it undergoes a reaction to give the enzyme and the product in the second step. So ES formation will equal K1, right? So that's from the first step here when the enzyme comes together with the substrate. So the reaction constant K1, then concentration of the enzyme, right, times concentration of the substrate. So it's second order reaction rate. But then the concentration of the enzyme, we use this expression here that we just wrote down above, K1. This will be enzyme total minus the concentration of the enzyme substrate complex. Like so. And times the substrate. All right, so that's how it's going to be forming. Now so this will be the rate, right? Then the rate of the complex breakdown. Complex breakdown equals, now once you have this complex here, right, there are two ways for it to break down. You can go back to regenerate the starting materials with the reaction constant K -1, or you can commit to the reaction and produce the product, right? So there are two ways for the ES to break down. So if you go left, the rate of the breakdown will be K -1 times enzyme substrate complex. And if you go right, it will be through the reaction. So the reaction constant K2 times enzyme substrate complex. All right, and here comes the key approximation of the whole thing. So basically the idea is that the enzyme substrate complex is that the rate of its formation and the rate of its breakdown is kept constant throughout the reaction, right? So in other words, if this, so just think about this. As the reaction proceeds, right? So you throw in some enzyme, you throw in some substrate, some of it is starting to form at the beginning, some initial time required for its formation. But then as this starts to accumulate, more and more of it will start to break down until it reaches a point when the rate of the breakdown of the complex is equal to the rate of its formation. And that's when the reaction reaches the steady state, right? The rate, basically the amount that is formed is equal to the amount that is decomposed. And that continues until the very end of the reaction, until all of the substrate is converted. So this is known as steady state approximation or steady state assumption. Steady state assumption. So the rate of the formation, K1, enzyme total, minus the concentration of the enzyme substrate. That's from here, right? From this part.
Sorry, where'd you point? Where it's from?
So this is so we equating the rate of the formation to the rate of the breakdown, and the rate of the formation is here. So rate of the formation equals the rate of the breakdown, and the rate of the breakdown is here. Now, so there are a number of algebraic transformations here, which you can, this is not a math class, so we don't need to go through that, but they are, look on page 200 in your textbook, okay? So basically this expression is solved for the concentration of the enzyme substrate complex. And that equals, if you solve it for that, you can see there are actually three different rate constants. There's K1, there's K -1, there's K2, right? So they all present in our original formula for how this enzyme will work. So the concentration of the enzyme substrate complex will equal enzyme total Again, the enzyme total is the total amount of the enzyme present in the reaction mixture, which means the enzyme which is bound to the substrate plus the free enzyme. Substrate concentration And the idea was also not only to solve it for the enzyme substrate complex, but also combine all the rate constants together, because these will obviously will not change. Like so. So this term, these three constants together, okay? So the three constants together is, if you combine them all into one unit, this is known as Michaelis constant, Km. K negative 1 plus K2 divided by K1. Michaelis constant. Michaelis constant. And so with this, then we can rewrite the our expression. Let me insert another slide. I'm going to upload this after the lecture so that you also have the math. So the concentration of the enzyme substrate complex equals, again, the enzyme total times substrate concentration Km plus substrate concentration. So all of that is now, you can see, condensed to a very small expression. We can simplify it even further. Now, again, remember that the initial velocity is what we're looking for. It's going to be, from the previous slide, K2 times enzyme substrate complex. And so from the expression above, V naught is K2 enzyme total substrate Michaelis constant substrate concentration And now imagine, let's introduce another parameter. Let's introduce another parameter, Vmax. Vmax maximum velocity. Now, the concentration of the enzyme is, so the enzyme is the limiting factor here. Now imagine that all the binding sites on the enzyme are occupied, right? So the enzyme cannot accommodate any more of the substrate. Then you reach the maximum rate, right? So the rate is as you increase the concentration of the substrate, you cannot raise the reaction rate anymore. So let me quickly draw this. I think graphical representation is the best. So let's say if this is the substrate concentration, right? This is the initial velocity, V naught. So there is a point of what's known as saturation, right? So basically it's maximum velocity. And so as you start the reaction rate goes up as you increase the amount of substrate, but then it doesn't matter how if you increase the substrate concentration or not, you cannot increase the reaction rate anymore because you have saturated the enzyme, right? So the enzyme, let's write this down. That's the key. Enzyme is saturated. You cannot increase the reaction rate because all the active sites are taken. And so that will happen if let me see. That will happen when the concentration of the enzyme substrate complex equals the concentration of the enzyme total. So in other words, there is no free enzyme left in the solution. All the enzyme is fully saturated with the enzyme substrate complex. Then Vmax can be defined as K2 on the concentration of the enzyme total. And then the expression takes the expression that will reach the final form, and it's going to be V naught equals Vmax maximal rate times substrate concentration Km plus substrate concentration. So we reached what's known as the main equation of the enzyme kinetics, known as Michaelis-Menten equation.
So is that really the only one we need to use? We don't need to use the other ones?
We don't need to use the other ones. What do you mean? Which the other ones?
The other equations on this page and on the other one.
Well, this is just derivation of the, I just introduced, I mean, using this math that I showed to you, I introduced all the key parameters and we basically derived this equation.
Okay, so this is the actual active form of the equation that we're going to use.
Right, and there are different forms of this equation that we're going to discuss. That's right. But you need to understand what each parameter in this equation means, right? So if I ask you what is Km, you need to be able to tell me what Km is, what is Vmax, and what is the meaning of the Vmax. When I ask you about substrate concentration, you have to tell me that it's a substrate concentration which is at the beginning of the reaction and not at some point during the reaction. What is V naught, right?
So earlier when you put when concentration of the ES complex equals the E total, what does that mean again?
So that means that the enzyme has reached saturation. So in other words, all the enzyme in the system is fully saturated with the substrate. So there is no free enzyme left, which means the enzyme is working its maximum capacity. You can't make the reaction go faster by increasing the substrate concentration anymore.
The same thing that the Vmax equals K2 ET.
Yeah, so that the enzyme reaches maximum velocity. Or the reaction reaches maximum velocity. All right, so there are a couple of slides that are kind of the summary of what we just talked about. Let's briefly go over them. So, this is the equation we used. Enzyme total, again, it's the concentration of the free enzyme plus the concentration of the enzyme substrate complex. And now substrate total, we also assumed that since we measure initial velocity, so the substrate concentration of the substrate is the concentration of the substrate total, right? Because very little of the substrate has been consumed at the beginning of the reaction. And so we don't need to worry about the some of the substrate that has reacted to give the product. Now steady state assumption, rate of deformation minus rate of the breakdown equals 0. Observed rate of the breakdown, rate of the breakdown of the product. So we have that. And finally, we have this Michaelis-Menten equation. Now, something that we need to discuss further. Kcat, what is Kcat? Michaelis-Menten, you already know. Michaelis-Menten constant, sorry, Michaelis constant. You know the Vmax, right? When all of the enzyme is in the enzyme substrate complex and is dependent on the breakdown of that complex. And depend, okay. So for kinetic measurements, how do we do these kinetic measurements? Let me see. So this basically slide just, what does it tell us? So how would you do an experiment? So you mix the enzyme and a substrate, okay? You record the rate of substrate disappearance or product formations, it doesn't matter. Remember, when you do the reaction kinetics, you can follow it by substrate disappearance or product formation. So nowadays, you know, instruments such as high performance liquid chromatograph, HPLC, right? You can use that for, you don't need to have, let's say, fluorescent substrate or luminescent substrate to follow the absorption of light as a way to record the substrate conversion or product formation So nowadays with the liquid chromatograph, you can very easily integrate the peak corresponding to the substrate or the peak corresponding to the product, and find out how much of the substrate has reacted, how much of the product has reacted. All right. So record the rate of substrate disappearance, function of time, plot the initial velocity versus substrate concentration, change substrate concentration, and repeat. All right, so we'll get to that. So why do we need to change the substrate concentration? And so here is the, so when you mix things together, you have to allow for what's known as dead time between mixing and the start of the measurements, right? So this because of the diffusion. So you have to give all the reagents some time to diffuse together and produce equal homogeneous concentration in different parts of the reaction flask, right? So here's your initial velocity. That's where you start working on it, right? It's the very beginning of the experiment. And here you can see the velocity will change because the substrate has reacted, and this portion of the curve is already not as useful because you cannot use the initial substrate concentration in an unchanged form. Okay. So effect of the substrate concentration, deviations due to limitation of measurements, substrate inhibition. So limitation of measurements. So so now these days, as I mentioned to you, the instrumentation is actually, it's very expensive, right, to actually to do these experiments, but the instruments themselves, they provide you with high precision data. So in the past, this was also an issue because the error margins were pretty large. Substrate inhibition. So let me think about it. Substrate inhibition. What is this? Basically, let me think about it. I'll put this in this homework for me. What exactly this means. I mean, I've heard of this before, but now I can't remember. Okay, and this deals with inhibitors. So we'll talk about this later. All right, so as far as Km, let me put another slide in here. Insert another slide. So where do you get these Km and Vmax? How do you calculate them during these kinetic measurements? So you do this through what's known as a Lineweaver-Burke equation. Lineweaver-Burke. we're kind of running out of time for this, but let me briefly show you. So let's say you have your Michaelis-Menten equation, right? V naught equals V max times substrate Km plus substrate. So what we're gonna do, we're gonna take a double reciprocal of this equation. So what we're gonna do is we're gonna put the numerator and denominator. Vmax substrate. And then break this apart into Km over Vmax reciprocal substrate and plus 1 over Vmax. Then if you perform the experiment and if you, so let's say this is your plot like so. On the x-axis, you will have the reciprocal substrate concentration. So basically you vary the substrate concentration at the beginning of the experiment, and you take the reciprocal and plot against the on the x-axis. On the y-axis, you're gonna be measuring the reaction rate, and you're gonna be plotting the reciprocal initial velocity. Okay. So then look at this equation here. If this basically is what is y equals kx, right? Oh, sorry, ka plus, how do you go? My math skills are not very good, but I think it's, and it's correct. Is it C here? What
B.
letter is used?
Are you looking for the slope equation?
The slope. What's the slope equation?
Y equals mx plus b.
Y equals, what is it?
mx plus b.
Mx plus b. All right.
Yeah.
Y equals mx plus b. And that's what we have, right? We have the slope equation where this is the x, right? This is b, and this is m, and this is y, correct? And then you get the slope. And the slope is what? Is Km over Vmax, correct? Correct? Slope equals Km over Vmax then y-intercept is 1 over Vmax and x-intercept is negative 1 over km. You even have more data points than you need, right? So you perform the experiment. Again, you start with different starting concentrations. You measure the velocity. You take the double reciprocal of both of these numbers, plot a graph, measure the slope. From the slope, you get the ratio. From this intercept, you get the reciprocal Vmax. From this intercept, you get the negative reciprocal Km. So basically you can calculate the kinetic parameters using this Lineweaver-Burk approach. Okay, so on sapling, I think there are a couple problems actually, which give you some of these numbers, right? They give you some substrate concentrations and some velocity. So what you will need to do, you will need to plot a graph and calculate these parameters.
Do we actually, sorry, do we actually need the x-intercept though? No, right?
No,
It's
as
just
I
extra
said,
information?
yeah, you have even more points than you need, right?
Okay, yeah, okay, thank you.
You don't even need the slope. You just need the 2 intercepts. Slope is just you can just is to validate your initial calculation, right? Does it make sense? All right, so please, I'm gonna give you some reading. Now, I told you about the derivation of this, but read what we just discussed. Again, it's the type of material that actually would be useful to listen in the lecture and also read in the text. And it's only actually 4 pages. And on in the lecture on Friday, we're going to continue working with Michaelis-Menten equation and apply it to inhibition, enzyme inhibition. Sounds good?
Yeah.
All right, guys. I'll put the lecture on YouTube. As usual, any discussion is welcome on Canvas. See you later.
Thank you.
Bye.